In section 7.4, we're going to look at a concept called the bond energy and see how it's related to energy changes during chemical reactions. When atoms form bonds, they obtain a lower energy. That is to say, that forming bonds results in a release of energy. If we were to do the opposite process, that is to break a chemical bond, it makes sense to note that it will take energy to break a bond, well, because it's the opposite of bond formation. So the energy required to break a chemical bond is given a specific name. It's called the bond energy, and you can find extensive tables of average bond energies in your textbook and in other places as well. So energy changes for chemical reactions are normally expressed in terms of the enthalpy change for the reaction. And we can use the tabulated values of average bond energies to calculate the enthalpy change of any reaction. And it should be noted that this is the symbol that we give for the enthalpy change of a reaction. We normally say that this is delta H. How we calculate the enthalpy change is this. We're going to sum together the bond energies of all of the bonds that we're breaking, and then we're going to subtract from that sum the sum of all of the bond energies of the bonds that we're forming. So just pointing out here that the symbol uppercase sigma means to add together a collection of things. So here's a little example. It says use bond energies to calculate the enthalpy change for the reaction 2H2 plus O2 gives 2H2O. So the first thing that you want to do is write out the Lewis diagrams for all of the reactants. And these are the bonds that we're going to break. And then you want to write out all of the Lewis diagrams for all of the things that are in the products. And these are the bonds we're going to form. And then to calculate the enthalpy change, we just use our little formula. So you can see here that the bonds that we're breaking, well, we're breaking two hydrogen-to-hydrogen single bonds. So 2 lots of 105. And we're breaking one oxygen-to-oxygen double bond. So we've got one lot of 119. We're going to subtract from that the sum of all of the bonds being formed, and we can see that we've got 1, 2, 3, 4 oxygen to hydrogen single bonds that we're forming. So we've got 4 times 110. So when we put all of that together, and we just enter it into the calculator exactly as I've written out there, we get the answer of negative 111 kilocalories per mole. And we know our units are kilocalories per mole because that's what was given in our table. So in this case, we have a negative enthalpy change. And enthalpy changes can be either positive or negative. Normally, once we've calculated the enthalpy change for a chemical reaction, we'll write it at the end of the equation in this form. As I pointed out, this particular enthalpy change is negative, and the negative enthalpy change indicates that heat is lost during this reaction. And reactions in which heat is lost by the reactants are described as being exothermic. And exothermic reactions will always have a negative delta H. Exothermic reactions produce heat as a product. This heat is released into the surroundings And you can recognize that you have an exothermic reaction because it will raise the temperature of the surroundings. So just summarizing, if a process is exothermic, it will have a negative enthalpy change. Because heat is being released in this reaction, the surroundings will get warmer. Some reactions are what we call endothermic. They require heat as a reactant. They will always have a positive enthalpy change. As endothermic reactions take heat from the surroundings, they will lower the temperature of the surroundings. And just once more, the key giveaway that a process is endothermic is that it will have a positive enthalpy change associated with it. So summarizing all in the one diagram, endothermic processes have a positive enthalpy change. They take heat from the surroundings, which results in the surroundings getting colder. So here's an example from the book. It said, is each chemical reaction exothermic or endothermic? And we can see in reaction A that heat is a product, and that means that in A, heat is leaving the system and going out into the surroundings. So this means that A, because heat is a product, is exothermic. In B, we can see that heat is a reactant. It is being consumed by the system, so it is being taken in by the system. So because heat is a reactant, the reaction is endothermic. Another way of indicating whether a reaction is endothermic or exothermic is to use what's referred to as an energy level diagram. In one of these diagrams, you'll have energy on the y-axis and progress of reaction on the x-axis. We'll have our reactants on the left and our products on the right. In an endothermic process, energy is being absorbed, and so for this reason, the products will always be at higher energy than the reactants. If we have an exothermic reaction, energy is being lost by our reactants or released by our reactants, and so for that reason, our products will always have less energy than the reactants. And that concludes the section on bond energies and chemical reactions.